first energy level is really small. It hardly has room for electrons at all. An S sublevel is all there is. 2 electrons that constantly whiz. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. A little bit larger the second shell, 2 sublevels there and do dwell. An S sublevel that maxes at 2, and a 6 for a P if that's okay with you.
It's okay with me.
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. The third shell is even larger still, an S and a P top the bill. D sublevel is added on top, 10 electrons can fit at above. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. The fourth shell is the largest yet, an S and a P and a D, I'll bet. An F sublevel is also seen. How many electrons? Up to 14.
14, that's a lot.
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10.
Electrons are found outside the nucleus. They sit around in energy levels, which are made up of sublevels, which can then be broken down into orbitals, and 2 electrons per orbital. Each one has opposite spin. Woo, 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 woo.
And it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10.
Why does 4s fill up before 3d? Because the force is enormous, you see.
I see.
Overlap 4s has less energy than the supposedly lower 3d. 3d, I love seeing in 3d.
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10.
The overlaps increase in frequency.
Oh.
4f fills up way after 5p.
That's weird.
Keep track of the overlaps really cool.
Oh.
You just gotta use the
Diagonal
rule. I love the diagonal rule.
And 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10.
I can't wait, just tell me when.
Get them all up, let's start again.
Again, one top level fills and the next can start. Electron config is
Something that I heart.
Oh yeah. And now
It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10.
Okay, you can stop now. Wait, oh my gosh, your space is turning around. Oh.
Welcome back. I hope you enjoyed that song. It's very, very informational. It's very, very annoying. So I hope it bothers you enough for you to remember that. By now you should be back and finish with the electron configurations. I hope you already got that order of things. Know how to follow the diagonal rules and knowing how to fill in the electrons. So just a quick review here. S suborbital can hold how many electrons? 2. P suborbital can hold how many? 6. D suborbitals can hold 10. And F suborbital can hold 14 electrons. Okay? And the order it goes diagonal rule: 1s, 2s, 2p, 3s, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. There you go. That's kind of the order. If you remember from the song, that's the first few, and it does follow the diagonal rule. And we fill in electrons depending on how many electrons there are. So, you should have, following the next sheet, today you'll learn about this thing called the noble gas configuration. Noble gas configuration. Okay, noble gas configuration. Oh, smokes, this did not print out right. Uh-oh. Oh, wells. Alright, noble gas configuration. Noble gases, where are they located on the periodic table? Noble gases are located on this column right here. Okay, what do you know about noble gases? They don't react. Good. They don't react. Why do they not react, you say? Because good. Outer shell is full. Outer shell is full. Okay. They have 8 valence electrons except for helium. Helium only 2 valence electron on the outer shell. Everybody 8 valence electron. 8 valence electron. 8 valence electron. So everybody's 8 except for helium because it's only got 2. But remember, the first energy level, all you need is like a helium, the nucleus is in the middle there. It can only hold 2 electrons on the first energy level anyways. That's why it's a full level on the first energy level. Full level of electrons. Okay? So noble gas. For example, helium. Let's do the noble gas for this. Helium is 1s2. Neon is 1s2, 2s2, 2p6. Okay? Argon, the one on the next row, 1s2, 2s2, 2p6. After 2p is 3s2, 3p6. Okay? So take a minute to do the configuration for krypton. Pause the video, do it for krypton. 1s2, 2s2, 2p6, 3s2, 3p6. And then after 3p is 4s2, 3d10, and then 4p6. And then xenon. Now on the next one, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. What's after 4p? 5s2, 5s, and then after 5s is 4d10, and 5p6. Okay? And then radon. Oh my goodness. So radon's a little more complicated here. We better get our diagonal rule ready. Radon is on row 8, 86 electrons. Okay, 86 electrons. It's a little trickier because it's a lot longer. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 3d after 3d is 4p6, 5s2, 5s2, 4d10, 5p6, 6s2, 6s. After 6s is back to the line is 4f. This is new. 4f 14, 5d10, and then 6p6. Okay, there you go. How do I know that? It's pretty simple. Back to the P block earlier. We know that these are all 2p6, 3p6, 4p6, 5p6, 6p6. So I simply just went all the way to the p6. Right? Just follow the diagonal all the way to p6. If you don't trust me, you can count all the electrons, add them all up. 2 plus 2 is 4, 4 plus 6 is 10, 12, 18, 20, 30, 36, 38, 48, 54, 56, 70, 80, 86. Voila. Pretty cool. Yeah, I don't expect you to count as fast as I do, but noble gases, look at these. What do they have in common? Other than helium, they all have an ending of something p6, 3p6, whatever the row they're on, 5p6, 6p6. Okay? So instead of, noble gas configuration is nice, because instead of having to write all these over and over again, we can use noble gases as shortcuts. Okay? And you appreciate this. You actually like this. And I'll show you why. For example, calcium here. Calcium, the electron configuration is 20 electrons. So 20 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6, that's 18, and then 4s2, right? So, do you identify a noble gas in there? The answer is yes. Look for a p6, right? So this is here. What is that? 1s2, 2s2, 2p6, 3s2, 3p6. And that is actually argon. notice you check that, you look at argon here, it looks exactly the same as that. See this whole, right? So for noble gas configuration, you can write in the argon, the gas, and then just tag on, add in 4s2 after argon, then you have your noble gas configuration. Okay? So that's the explanation behind it, but it wouldn't be a shortcut if you have to do all that and then figure out the noble gas, right? It would not. It means you're doing more work than you need to. So I'm just using that to explain why. So the next thing here is I'll go over the steps. Okay? So tellurium, Te. Find Te on the periodic table. This is Te right here, element number 52. I will walk you through this slowly and carefully here. To tellurium. Okay? Here's the rule. Step 1. Find the element. Find the element. Okay? And determine what row is the element on. So, what row is element on? So in the case of tellurium here, it is on row 5, right? Te is on row 5. So what you do is you go find a noble gas before that so that you can add on electrons to get to tellurium. Okay? You find a noble gas, again, find a noble gas before tellurium. So you go, number 2, you go up 1 row and use the noble gas at the end. Basically that row at the end. Okay, so use the noble gas from the row above. So tellurium's on row 5 here. Let me zoom out a little bit so you can see the whole periodic table. So tellurium's on row 5. So we're going to go up to the row before we use krypton. Okay? Krypton. So krypton, you're going to put krypton, so step 3 there. You're going to put that noble gas in the bracket. And because tellurium is on row 5, you're going to start with 5s. Okay? Knowing that krypton's already 36 electrons, okay? Krypton is 36 electrons, and tellurium, Te, is 52. We need to add electrons until we get to 52. So we go back to the diagonal rule. We're at 5s. 5s2. What's after 5s? 4d10. So that's 36 plus 2, that's 38. Plus 10, that's 48. We need 4 more. What's after 4d? 5p4. And this would be your noble gas configuration. Okay. With more practice, it becomes easier, and it becomes a lot shorter than the long electron configuration. All right. So these we still have to practice, and to prove that, here we go. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. What's after 4s? 3d10. 4p6, 5s2, 4d10, and 5p4. Okay? And so, find that noble gas in there. So here's a p6. So this is your noble gas right there. What noble gas is that? That's actually krypton. And we add in the rest, 5s2, 4d10, and 5p4. Alright, so from this point on, I'd like you to go ahead and try the electron configurations. Do these here. The noble gas configuration, noble gas configuration, noble gas configuration. You don't have to do the electron configuration if you don't want, but it helps show that. Okay, like nitrogen. It's got 7 electrons. So 1s2, 2s2, 2p6, 3. Is there a noble gas in there? Yes, there is. Because helium is the little exception there, the 1s2. So then you put helium in there. Not much of a shortcut here, but this is the noble gas configuration regardless. 2s2, 2p3. That is still nitrogen. Okay. So for chlorine. Chlorine, let's follow the rule earlier. Okay. Here's a nice handy dandy periodic table that you do need with you. I'm going to move this up so you can see. Where's chlorine? Chlorine is right there on row 3. So you will use the noble gas right above it, which is neon. Okay? Neon has 10 electrons. And chlorine have how many? Chlorine has 17 electrons. What row is chlorine on? Chlorine's on row 3, so you start with 3s2 and then 3p5. There you have 17 electrons. That's a noble gas configuration for chlorine. All right, for mercury now, the next one. Mercury is where? Element number 80. Find element number 80 here. We get a nice new color here. Element number 80 right there. What row is it on? It's on row 6. So you go back and you use the noble gas on row 5, which is xenon here. Okay? So you put xenon, Xe. Xenon's 54 electrons. We need to get to 80. How do you know what starts next? It's whatever row the element is on, it's the S of that. So it's on row 6, so 6s2. And then we continue using the diagonal rule. Where is my diagonal rule? Okay. Where'd it go? Where did it go? Nope. I don't know where my diagonal rule went. So anyways, I don't know where my diagonal rule went, but it's 6s, and then 4f14, and then 5f14. How much is that? 54 plus 2 is 56. That's 70, and we need to, mercury is 10. Mercury is 80, so then 5d10. Perfect. And it makes sense. Remember, this is the D block here. This is the D block. And it's element 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's element 10. And D's always one less in the S, on one less in the row. So it's 5d10. And that is the noble gas configuration for that. Complete the bottom part here using noble gas configurations. Okay. And I want to mention here uranium. Uranium is part of row. This is the last two rows on the bottom. This is row 6 and row 7. It's continuation of those. See, they brought it down here because if they didn't, the table would look really ugly if they stretch it out really far. So uranium's on row 7. You use the noble gas on row 6, which is radon. Okay, uranium, I'll give you a hint here. It's Rn for that, and then you continue 7s, yada 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 yada. Okay, so get that done. It is a lot of work here. So it is a lot, and oh my goodness, this bottom one didn't print out very well. Shoot, it's not supposed to be like this. There's an error on the print. Okay, so get that done. Pause the video, get that done, and then continue on after you finish. Okay, the bottom part here, electron configuration is just a sum up of everything. Nitrogen electron configuration is 1s2, 2s2, 2p3. Nitrogen 7 electrons, right? Yes, it is. So 2p3. Noble gas configuration. You go on the row above, helium. Nitrogen's on row 2, so you start with 2s2, 2p3. That's the noble gas configuration. And then you have to, that was supposed to be on the next page already. It didn't print out quite right. So it's still 7 electrons. Okay, you have to fill in the electrons using these orbital notation here. 1s, 2 electrons. Remember, they're opposite spin. You have one up arrow, one down arrow. 2s, we have, so the configuration, 1s2, 2s2, 2p3, right? The next one, s, again, you fill both of them. 2p though, there's 3 orbitals for p, so you got to go up, up, up before you can go down. Remember, 1 in each room before you start pairing them up. And this was Hund's rule. Remember, 1 in each room before pairing them up. And then opposite spin, it is Pauli exclusion principle. Okay. Aufbau principle is putting them in order using the diagonal rule. So for example, nickel here, 28 electrons. So you go 1, 2, 3, 4, up, 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 5, 6, 7, 8, 9, 10, 11, fill in 3s before you go to 3p, up, 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 and then you go down, down, down. 1 in each room first. So how many do we have so far? 2, 4, 6, 8, 10, 14, 16, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. And it should look like that. Okay. Again, 1 in each room, the whole orbital, before you pair them up. The last one needs to look like this. If you do it like this, if the d orbital is 5, 1, 2, 3, 4, 5, and you go 1, 2, 3, 4, 5, 6, 7, 8, and it is wrong because there's one empty one over here. You cannot have an empty one if you have pairs. There has to be something in there before you start pairing them up. Okay, so the correct one is the one I did on your paper here. You go ahead and fill those out. Fill those out and pause it. Complete this part up here, and then we'll go on to the next one. Okay. This next part right here is it's for pre-AP only, but it would not hurt if you are in a regular class and you're trying this. Always challenge yourself if you would like, but it's not required for you. Pre-AP students, this is required for you. Okay, electrons with ions. Remember, ions, we have cations, which are positive. That means they lost electrons, 1 or more electrons. Okay. Then you have anions. There's more n's here, so it's more negative. So it's negative. It gained electrons. Okay. So, number of electrons. Here is, for example, iron plus 2. It's positive, so it lost electrons. How many did it lose? Well, it's plus 2, so it lost 2. Okay, so if you look under your periodic table, nice handy dandy periodic table. I don't have any more nice ones because I drew all over it. So iron is right there. It's got 26 electrons, right? Iron has got 26. I'm just going to put it here for reference. But it lost 2 to become positive 2, so now we only have 24 electrons left. Okay? So boron here, it's got 5. It becomes positive 3, so guess what? It lost 3, so it only has 2 left. It's mostly positive, huh? Okay, look at number 6, oxygen. Originally, the neutral one have 8 electrons. But it's negative 2 because it gained 2, so then there's 10 electrons now. Okay? And then so you write the electron configuration for those exactly the same way. 1s2, 2s2, 2p6. What's this the same as? 1s2, 2s2. So oxygen minus 2 have the same number of electrons as a neon, right? Neon has 10 electrons. So iron plus 2. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 4, 3d4. Since it lost 2, originally it would be 3d6, but it lost 2 electrons, so now it's 3d4. Okay? So complete this page as well. Complete this page as well. You'll be just fine. And then this next one, 7 through 10. It's fairly simple. It may look a little weird, but it's fairly simple. So 1 S2, 2 S2, 2 P6, 3 S2, 3 P6, 4 S2, 3 D10, 4 P6. Okay. So number 7, how many electrons do we have? 2 plus 2 is 6. No, 2 plus 2 is 4 plus 6 is 10, 12, 18, 20, 30, 34. So we have 34 electrons here. What element is 34 electrons? 34 electrons. That's selenium. Selenium. Or let's use the symbol. Se. Okay. So it says choose 3 possible elements or ions. So we can pick here arsenic. Arsenic can gain 1 electron to be selenium, to be the same amount of selenium, right? So if it gains 1 arsenic, we can have arsenic minus 1. That'll be the same thing because arsenic is 33 electrons. If we add 1 more electron, okay, arsenic minus 1 will give you the same number of electrons. No, proton does not change. It'll give you the same number of electrons. Okay, and then the next one, or we can go bromine, right? It can lose an electron to become that. So bromine can lose 1, Br plus. And these ions aren't very real, but it's just to show you the number of electrons. Bromine plus 1, if you lose an electron, it will fall down to 34, just like selenium. Okay? So, do that. Complete this. If you have any questions, ask your teacher. Your teacher should have an answer key. And so, good luck. Have fun.